Let's start another session. Today's session will be focusing on convolution autoencoders for image denoising. So what exactly are we looking at? We are trying to understand the methods for image denoising. There are multiple methods to achieve image denoising. Either you can do cans and you can also do autoencoders. But there's one limitation with cans, that to utilize cans you need to have a complete denoised image. So that's the fundamental requirement. So let me show you one whiteboard. Or maybe we can use Excalibur also. Let's use whiteboard only. So basically image denoising via autoencoders. And before we move to segmentation models, it's better to learn what exactly is autoencoder and how autoencoders work. So we'll learn that in this particular video. So basically autoencoders, or the task at hand, is image denoising. This image denoising can be performed via two ways. Either you can use autoencoders, advanced versions of autoencoders are known as VAEs, variational autoencoders, quite advanced, and the other method is GANs. So in autoencoders, let's say you are using autoencoders. So if you are using autoencoders, then what happens is you take an input image. This is your neural net, bunch of convolution layer. It decreases the size of the convolution layer. The smallest layer happens here, then upscaling happens until you reconstruct the image. Let's say image size is 256, 256. I'm assuming that you know that a convolution layer would decrease the size of the image into a smaller representation, because a convolution layer fundamentally is feature abstraction. You must also remember the formula n minus f minus 2p by s plus 1. So by this you can also verify that the final size of the dimension after any convolution layer is a reduced version of the original, usually the reduced version, until unless f and p are set to 0 and s is set to 1, or maybe something like that, n minus f plus 2p. Maybe this correct me if the formula is wrong. Basically you got the idea. So basically we want to construct the same dimension, 256, 256. Also here we want 256, 256. How do we do that? We can do that via autoencoders. The autoencoders would do, you construct a lot of convolution layers and then you reach the last convolution, then you do upscaling via conv2d transpose. So convolution 2d feature extractor, whereas conv2d transpose it feature extrapolator. What does it mean? Basically conv2d transpose, if you have this 1 2 3 4, if you want to extrapolate it from 2, 2 to 4, 4, so this was your original 1, this was your original 2, this was your original 3, this was your original 4. So what you can do is you can either have duplicate here 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4 4, or you can do set it to random variables, and based on this you can learn the parameters, that the actual parameter should be what the actual parameter should be. So there are multiple methods. Now talking to the other method to achieve image denoising, which is GANs. So what we can do is you can train a pix to pix model, but for this the fundamental requirement is you have noisy image. Along with the noisy images, you have, for every noisy image you should have a denoised image. So let's understand what they are doing. So this example tries to implement a deconvolution autoencoder for image denoising, mapping noisy digit images from MNIST to clean digit images, basically from noisy data, image data, to clean image data. So the task is something like this. You have this noisy thing, and from this we want to have this particular thing. So how do we do that? The idea of autoencoders is to remove the details. Since we are using a lot of convolution layers, the lot of convolution layers will try to extract the features. So the main features are not dots, rather these lines. And then conv2d transport would try to reconstruct the original image using those features. Since these were not captured as the main features, obviously would never be captured as the main features. So the reconstructed image would be a clean denoised image. That is this. So that is the fundamental idea. Now in this section of code, they are actually trying to construct the data. So this particular data, they don't have noisy image data set. So what do they do is they try to load the MNIST data, then add random noise to it using this particular method, and they try to display that the training data would be something like this after adding noise to it. So they don't have a noisy data, but they construct a noisy data. But in case you have a noisy data, let's say you are procuring satellite images, or let's say you are procuring camera images, those might be sometimes noisy, or let's say you are procuring images at night time, those might be noisy. So either you can go with autoencoders if you don't have the corresponding denoised images, or if you have a corresponding denoised images, definitely go with pix to pix scans. But if you don't have, then go with autoencoders. And the idea of autoencoders is a lot of convolutions would act as the feature extractor, and the main features are not these minute details, because the noise is a detail, is a minute detail. So as a convolution would not extract a detail, but would extract the feature, and the feature is this line and this line. So those features will be extracted, and when you do the conv2d and you try to reconstruct the image using conv2d, denoised image would be constructed. So that is the idea, main idea. So let's understand the architecture here. We have an encoder and we have a decoder. It consists of two parts: encoding of the image, which finally goes to the decoding of the image. Encoder has conv2ds and decoder has conv2d transpose. Just a sec. So that is the fundamental idea of this. Although the architecture is quite simple and basic in it itself, is not quite fundamentally complex, we can just quickly take a look at it. So the image size for MNIST is 2028, and there's one channel, so 1. So we have an input. Dimension of the input is 28.1. This input is going to a convolution max pooling. I hope you have an understanding of convolution and max pooling. If you don't, then don't worry. I'll be coming up with a complete course, beginner to advanced, of computer vision. There you can learn about it. So assuming that you know what a convolution 2D is and max pooling is. Pooling, it again goes to convolution, then max pooling. All of these are feature extractors. Now after the feature extraction is done, it is assumed that all the minute details, which is aka the noise, would not be captured. Now we are trying to reconstruct the image using convolution 2D transpose. So for that we need two convolution 2D transpose. The number of convolution 2D transpose depend on the number of convolution 2D layers used in the encoder. So two convolution 2D used in the encoder. Similarly, we will use two convolution 2D transpose. Now once we are done with that, the last layer would be convolution 2D, this, wherein it would be a one channel, or which is the output layer, one channel, and the activation would be sigmoid. Reason being, you need a binary image, black and white image, so sigmoid activation, and thereby it will be the final output layer. Once that is done, your autoencoder would be ready, and you can train the data using that. Once trained, you can obtain predictions. So let me quickly go through and run this data or the code example, and we can see that this particular thing is quite interesting. I hope you got the idea of what this particular thing tries to do. So this particular initial part of the code section might look quite intimidating, and we can discuss that. Let me run the entire code. So AutoEncoder has two uses. One is image denoising. Other is image compressions. Image denoising, you must have understood that the minute details are not stored, and since the minute details are not stored, that can also help in compression, because the new representation would be consuming lesser space. So can be used for image compression. KNN is also used for image compression, KNN architecture, KNN algorithm, but autoencoders can also perform image compression and are slightly better. So if you are performing image compression, you won't be dealing with, so this deals with noisy data, let's try to see what goes in the input and what goes the output. So this is the model constructed. The model is trained on train and train data. What is the train data? The train data is nothing but MNIST data, which is the normal data. So there is no mapping happening. You have all the normal data. So this either you are passing the noisy data, basically you will be passing the noisy data. Whereas for image compression, you will be passing the original, irrespective of the fact noisy, blurry, sharp, contrast, hue, saturation, nothing, just original image, which needs to be compressed image. So is it a correct statement to say that this noisy data image will also be a compressed image? Yes, it is a correct statement. So let it run. Basically, I think you have got the idea of it. So this is how we are doing. So in the second run, what they are doing is, in the X they are passing the noisy data, and in the Y they are passing the data which has no noise, which is quite similar to your GANs, because in GANs also you would require the noise and denoised images, because you need to check whether or not the denoising was successful or not. So yes, GANs can also be used. because image denoising would require you either is one method is OpenCV method, or the other method is deep learning method. So GANs you have pix to pix. Pix to pix is a better one for noisy images, because you have a pair of noisy image and its corresponding denoised image. Don't we have a pair? I think we do have a pair. Like for every better to say, this was the original line of image data. From it we constructed a fake image, which is noisy image. So basically the statement is, for every noisy image you have a denoised image. So you can use pix to pix, GANs, or you can use VAEs. You can also use AutoEncoders. Here we are using AutoEncoders, which is quite simple to implement and fast enough for simple small image data. But if you have a very high resolution image data, let's say 256, 512, VAEs or GANs might not work as good as pix to pix. So that is how I would like to conclude, because all of them would require you, in the X they would require you the noisy input. What is X? X is basically what goes in. What is Y? What is expected or prediction, right? So in the Y you expect, this is the X, what goes in. Y is what is predicted or what is expected, and X will go in. X, with the X going in, it will make some predictions. Those will be matched with the Y. Loss calculations would happen. It would adjust itself, and finally the model would be trained. What is happening in this step? The noisy data is going in. Based on that, it gives a prediction that, okay, I think this is the denoised image. That is matched with an element of the corresponding element of the Y, which is the denoised image or the trained data. Based on that, the loss and values, all the values are calculated and updates are made. This keeps on happening for 100 epochs. Batch size is 128, which means that this particular data and this particular data is divided into chunks of 128. And then the calculation or the validation is based on a separate set of data, which is the validation data. I hope this helped. Stay tuned. And all right, let's catch up soon. Bye.